Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Materials research can draw inspiration from nature, but how do you approach this research when you're working with complex phenomena in a system that is almost chaotic? The key is to use a multidisciplinary approach. Patterns in biological materials such as shells result in enhanced material properties compared to what is traditionally manufactured by human ingenuity. New research has shown that similar complex patterning can be produced by carefully controlling a process known as frontal polymerization. Professor Nancy Sotos from the University of Illinois explains.
There are certain conditions, both chemical, where you change the formulation, or environmental, where you change the boundary conditions, and it can become chaotic. And so the key to this work is not letting it go completely chaotic. Really small changes in the chemistry, in the formulation, even just one ligand change in the catalyst, change the patterning and the material properties. The reason we can do that is because we're working on the edge of equilibrium.
The exothermic reaction is initiated by adding a chemical catalyst and applying heat or UV light. Localized heat generated by the reaction of the liquid monomeric solution initiates polymerization. The reaction then self-propagates. Carefully controlling various parameters, including the ratio of the catalytic initiator to a phosphate inhibitor, results in a polymerization front that is non-uniform.
Essentially, it just traverses in the X plane and then down in the Y. So you can think of it as moving in a zigzag motion, where in a test tube, you can actually see it spin around. That's just the heat diffusing to the cold spot.
That was Dr. Justine Paul, who completed this work during her PhD at the University of Illinois, describing the spin modes of the polymerization front in 2 dimensions. This spin mode is driven by localized heating that arises from the exothermic polymerization reaction, so it leads to hot and cold zones, and this is what gives rise to non-uniform crystallization. Both chemistry and the surrounding environment need to be considered to initiate this near-chaotic crystallization process.
Spin modes come because we pull heat out of the system, either through chemistry or the environment. There's this in-between zone where the instabilities occur. If you have lots of heat, it's hard to make it go unstable like this. But there's a window that we were guided by computations to find this window. And in there, you're generating just enough heat to move forward, but there's constant heat being lost to the surroundings. And that's what creates these beautiful modes of propagation.
Numerical modelling work was instrumental in identifying the transition from a uniform polymerization front to a chaotic or unstable one. Coupled reaction diffusion modelling showed that the different chemical catalysts have different effects, and that this must be carefully balanced by the amount of inhibitor. Small changes in the chemistry had a big effect on the stability of the polymerization front. The analysis of the kinetics was extremely helpful to understand the influence of chemistry, helping to pinpoint which polymers will produce patterning. If the polymer chains are aligned in the direction in which the load will be applied, the result is higher stiffness and higher strength compared to when the polymer chains are perpendicular. The domain size also has a role. As the domain size increases, the material is more amorphous and the toughness increases. Although patterning has been observed before, this is the first time that it has been precisely controlled in a way that enables the material properties to be controlled. This controlled near-chaotic polymerization process is a step change in materials fabrication. Usually, to produce patterns, an elaborate 3D printing regime would be developed. Controlling the chemistry and thermodynamics leads to a less deterministic or more natural self-assembly mode on a large scale.
There's obviously a lot of work on self-assembly and how things assemble, but that's on a very small length scale. These are kind of big engineering length scales at which these assemble and create these patterns.
The technique can be applied to other systems and could give rise to a new mode of 3D printing where some regions are patterned, applying hierarchical control to the structure in order to tailor the mechanical properties of a material. The numerical modelling and tuning of the chemistry are significant advancements. These results show what is possible through collaboration, as Dr. Paul explains.
This work wouldn't have been possible without a lot of the people who have contributed and collaborated on it. There was a lot of different viewpoints and expertise that really allowed this paper to come to its fruition, as well as kind of link some of those bigger property structure relationships. One, first understanding the chemistry space and how that imparts these patterns, but then, well, and I guess first even going back how that was guided by numerics, but then really deep diving into understanding the polymeric microstructures, as well as how those polymer chain orientations influence mechanical properties. That was really driven a lot by collaborations. Having different viewpoints on this allowed for those links to be kind of made a lot faster than we probably would have.
This work was published in a recent issue of Nature. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.